Okay, we're back and doing some mechanics with gravity. Um, as we all know, the old classical way of thinking about gravity is Newton's law of universal gravitation. This is also the reason why we have calculus. But what Newton figured out is what gravity depends on. He explained it mathematically. He never could explain why or how it works. That took Einstein. But we still use this for space launches, for putting satellites up. It's what we use to put people on the moon. We figured out the orbits and proved Kepler's laws for all the orbits around the sun, for example, and whatnot. And it's based on the inverse square law, and a great discovery in the history of science. And in particular, we're going to focus on the energy side of it, which is a little more difficult to understand. We're used to seeing, for potential energy with gravity and a lot of everyday problems, MGH. Works beautifully if you're talking about just, dropping things, roller coasters, things like this, where the height is very small compared to the size of the Earth. But for space launches and orbits and satellites and planets, we need something better because gravity changes. The mg part of MGH isn't constant, and so we have to figure out, using calculus, how to do it right. So let's start from the basics, which is really his law of gravity, gmm over r squared. It is a vector equation. It goes as 1 over r squared. Now this is true for spheres and point masses. It differs, though, if the object is big and different shapes, but we're not going to worry about that right now. This r hat is called the radial unit vector. It's a reminder that, let's say we wanted to figure out the force on mass 2 in this picture. R hat would be from the big mass, m1, and it'd be pointing towards the object that we're looking at, which is m2. Okay, so it's kind of like a position vector, points to where you're looking at. Now the force on m2 is going to be towards m1. Gravity is always attractive. And so what we do is we put a minus sign in this equation. Negative forces, in the terms of these vector equations, are attractive forces. And as far as we know, gravity is always attractive. So what about the energy, though? Well, we've got this relationship between force and potential energy. Force is the negative gradient of potential energy. Okay, there's this negative derivative with respect to position. So if we want to solve for the potential energy, we're going to have to use an antiderivative. We have to integrate. Okay, it's the negative integral of the force, which is negative gmm over r squared. We'll bring that dr up. And what this does is the minus signs take care of each other. Big G, m1, m2 are constants. And so we have the antiderivative of 1 over r squared, which happens to be negative 1 over r. So the potential energy, the attractive energy between two objects, is negative gmm over r. This is what we use for gravity, in big distances. Okay, I always get a kick, and my kids get a kick out of Buzz Lightyear and To Infinity and Beyond. But what you never hear them talk about in the cartoons is, how fast, how much energy does it take to actually get to infinity? This is exactly the question that we talk about when we talk about escape velocity. Okay, so what does it mean for the gravitational energy to be negative? Well, it's very similar to what we do with MGH. Okay, in everyday problems, if you want to figure out how high something is, you have to define where your zero height is. Okay, that becomes, you need a reference point. If everything's measured from that reference point the right way, you can get things to work out. So what this means in the gravitational sense is, let's say you've got the Earth, okay? And according to our new expression here, gm1, m2 over r, where is this 0? Well, it's 0 when r approaches infinity. In other words, when you're far away. Now, this is kind of weird because let's say if we're looking at the Earth, we're the Martians looking and the spaceship shoots off going sideways relative to us. Okay, so far away we're saying that your energy is 0. But at the same time, the height above the Earth is getting really big. So as your height increases, U increases. Okay, it's just like MGH. The higher you go, the more potential energy you have. Okay, that still holds true. Now the thing is, what that means is that the highest height you can be above the Earth is far away, or infinity. So this 0 energy is your maximum energy. Now since you can never really get to infinity, an infinite distance above the Earth, you're always less than infinity, that means you're less than 0. So your energy is always negative. It's an abstract kind of thinking, but that's what we're talking about. Infinity is your ceiling. That's your 0 reference point. It's like saying the ceiling of the room is 0 height. And so, since you can't actually rise up and touch the ceiling, your energy is less than 0. It's negative. Okay. Now, what that means for your total energy is kind of cool, because total energy is potential energy plus kinetic energy. Now, in this context, your potential energy is always negative. Kinetic energy, on the other hand, because you have your velocity squared in there, is always positive. So what this means is that you have 3 possibilities. You could either have your total energy be positive, if you're going really fast, let's say, and your kinetic energy is bigger than your potential energy. I suppose it could be 0 if they're equal to each other. Or your energy, if gravity wins, if you have more potential energy than kinetic energy, your energy would actually be negative. Okay? So the 0 point is kind of a threshold, if you think about it. If gravity wins, if your energy is negative, we call this the bound state. In other words, you're not going fast enough to break free from the Earth or whatever it is you're trying to escape from. The gravity is going to slow you down, stop you, and then pull you back. Okay, if you're in an orbit, for example, you would be bound by gravity. Your energy should be negative for that. Now, on the other hand, if your energy is positive and you're going really fast, more kinetic energy than there's gravity, gravity can't pull you back. And you've broken free. So if you wanted to travel to another planet or to another star system, you'd have to break free from the Earth or from the Milky Way. You'd have to reach a certain speed in order to do that. The threshold is what we're going to use to find what we call the escape velocity. What's that magic speed you have to exceed to break free from gravity? So that happens if your total energy is 0, which means that your kinetic energy and potential energies are equal to each other. Okay, now let's say, in this case, for the r value, we're going to use the radius of the Earth. Let's say you want to break free from the Earth. So one of the masses would be the Earth's mass. Your mass, the mass of your spaceship, would drop out, and if you solve for the speed, which we're going to call the escape velocity, that turns out to be the factor of 2 comes up, 2 times our gravitational constant, the mass of the Earth, all over the radius of the Earth. And you can plug numbers into that and you can figure out your speed. This turns out to be something like somewhere around 11,000 meters per second. Okay. It's pretty fast. Another cool thing you can do with this is, what if you set your escape velocity equal to the speed of light, and we can still use the Earth if you want, and solve for r. If we do this, you're going to have something like 2 times our gravity constant, the mass of the Earth, all over the speed of light squared. If you plug the numbers into this, you'd have what's called the Schwarzschild radius. And you're starting to get a sense of how far you'd have to scrunch something down to turn into a black hole, where the escape velocity is the speed of light. It's just kind of a fun thing to do. If you put numbers in for the Earth, for example, you'd get something like a centimeter or something like that, about the size of a marble. You'd have to scrunch the Earth down. You know, have all that mass in the form of a marble, and it would form a black hole. So it's kind of a fun thing to think about. Everything would have an escape velocity. Moons and planets and stars, and even your body, I suppose, you could figure out what the escape velocity is. But it all comes from the fact that we're talking about energy. This negative energy due to gravity, whereas kinetic energy is always positive. Our reference point is far away, and since you can never reach that and reach that maximum energy of 0, your energy is always going to be less than 0. That's the minus sign. Okay. This all comes from Newton's law of gravity, and from this attractive force. And in the end, these are the types of quantities and the expressions that astronomers would use and other people when they do their business. So I hope this gives us a better understanding and a little bit of insight into how gravity behaves and how we deal with it. And until next time, we'll see you later.